Right. We are Team Scientific Atlanta Reloaded, and our project is based on optimizing water evacuation with LST or laser surface texturing. This is an introduction of our team, and I'm Samuel Sahode, and I'll be the one responsible for delivering this presentation to you today. So before we break into our project and what we've been working on, we should discuss the background of what Conair does and why this matters. So Conair is a developer of commercial door thresholds and windows and other type of commercial facades, and they want to investigate how LST or laser surface texturing affects water drainage. LST is a new technology that's been developed that can make surfaces either super hydrophobic or super hydrophilic, and Conair wants to investigate how this can help with water evacuation. Obviously, water evacuation is very important because water retention inside of these commercial facades can lead to a variety of issues, including water corrosion and water damage, and this ultimately leads to costly repairs. So our objective as a team is to evaluate the impact of LST or laser surface texturing on water evacuation, and we'll do this by constructing a test fixture and comparing water evacuation between both the LST treated samples and the non-LST treated samples. So here we have the four samples that are provided to us by Conair. They provided us samples 1, 2, 3, and 4. Samples 1 and 2 are anodized samples, and samples 3 and 4 are powder coated. And essentially, we just broke down in these pictures. We tested the hydrophobicity of the surfaces with water droplets, and we were able to determine which zones were tested with LST versus non-LST, and we essentially broke down each of the samples into different zones based on these characteristics. Similarly, we have the surface properties, which are very important throughout the duration of the experiment. A hydrophilic surface just refers to a material that has a contact angle between the water droplet of less than 90 degrees, while a hydrophobic surface has a contact angle greater than 90 degrees. In these pictures, you can see we have a hydrophobic surface on the left and a hydrophilic surface on the right. This is from sample 1, zone 1 for the hydrophobic surface. For the hydrophilic surface, this is sample 4, zone 4. And you can tell based on the images that how the water sits on the surface. And we were able to capture these pictures and then process them in a software called ImageJ. And by doing this, we were able to determine whether each surface was hydrophobic or hydrophilic and characterize it appropriately. So we had a few questions that we wanted to investigate throughout the duration of our Capstone experiment, and we designed our experiment around these. The first question we wanted to know was whether or not LST is effective in evacuating water out of the door and window thresholds. The answer that we found was yes, it does help with water evacuation, which I'll get into later in the presentation. And we found that it helps by increasing the capacity of the reservoir and can sometimes decrease the startup time. That was the second question that we answered. And we also wanted to know whether or not the LST maintained a constant surface property, and we found that it does not. So going into our solution, we designed this test fixture. So our innovative test fixture, we have all of these different components. We have the water reservoir, which is where we were holding the water that would go through the system. We held up to 6 gallons at a time. The entire fixture was constructed out of a 2x4 frame. We had openings right here in the reservoir for draining the. We had a drain for where the water was dispersed from, and which would be dispersed into the piping network. We also had flow meters, which could adjust the flow rate of which the water would move through the system. We have this plywood platform where the sample is slid in and slid out. We designed it so that we could easily slide in and slide out different samples because we had 4 samples to test with. We also had adjustable feet for which we could level the surfaces and make sure that our sample was leveled. And we had 2 graduated cylinders in which we were able to collect the water that was leaving the sample at the exit point. And we have a short video over here of which the just shows how the sample works and how our test fixture works. So here we're opening the pipe network, and then as soon as we open it, the flow rates which have already been set before opening the network, which controls the flow at which the water leaves, and we have the water leaving the system and flowing through the system, both the LST and the non-LST side, and exiting right here into the graduated cylinders. And we're able to record factors such as the startup time and the reservoir height, which I'll get into on the next slide. All right. So as I mentioned previously, our test fixture was designed so that it could be easily replicated with each of the different samples. So here we have one sample going in and going out. You can see how easily it slides in, and we did this through the use of the T-slots, which we designed and attached to the fixture, and the sample could come out very easily as well. We also designed that our experience would be very modular so that we can enable future tests if needed, and Conair can also conduct future tests. And here we have the an example of the reservoir height being measured. And I'm not sure if the video wants to work. Essentially, as the water fills up, you can see that these little markings right here, instead of using a ruler, there we go, now it's working. Instead of using a ruler, we mark these little indentations on the acrylic panel that we implemented, and you can see that as the water height increases, it's very easy to measure how high the reservoir height is, and these go up in millimeter increments. So we made a few conclusions based on a test that we did run. We determined that the LST in general resulted in lower reservoir heights, which I just mentioned, for any given flow rate compared to the non-LST sample. So non-LST slides. So this means that they can handle much higher flow rates before overflowing. These flow rates would indicate to depending on the severity of a storm that was coming down, for example. So we also found that in general, the LST surfaces tended to be more hydrophobic than the non-LST surfaces, which tended to be more hydrophilic. Although we didn't have an indication between the actual hydrophobicity of the samples, which this was measured through the contact angle measurements that I mentioned earlier, we still found that the LST surfaces were more hydrophobic, and that hydrophobic surfaces can exhibit the lower reservoir height and faster startup time, which is what you want, compared to the hydrophilic surfaces. There could be some explanation for why this correlation wasn't found directly with the contact angle, but during our test, we did find that the LST was generally helpful in maintaining the lower reservoir height and the just in general better water evacuation. So that's a summary of what we've been working on so far in the project. Thanks for listening, and I really appreciate it. Thank you.